All right, I'm going to take a few moments to review activity A before we begin activity B. Our primary focus today is on pressure relationships, but let's review the volume relationships from yesterday. Yesterday, when we increased the temperature of a gas, what did that do to the volume? It increased. So increasing the temperature of the gas increased the volume of the gas, which means that temperature and volume are directly proportional, right? As temperature goes up, volume goes up. Then we looked at volume relationships with pressure. When we increased the pressure, what happened to the volume? It decreased. Yeah, in fact, when we doubled the pressure, the volume cut in half, which means, how are they related? They're inversely proportional. Volume goes up as pressure goes down and vice versa. Then we took a look at the number of moles, or the amount of gas. Okay, and one of the first things we did is we changed the type of gas from hydrogen to helium to nitrogen, and we saw no real effect on the size of volume. The volume didn't change. In fact, just kind of reminding you about how that looked, you can see the volume is set at 22.4 liters. If I change it from hydrogen to helium, the volume doesn't change. It's a slightly bigger gas molecule, but the volume doesn't change. Change it to nitrogen, which is 14 times bigger. The nitrogen might be moving slowly, right? It's moving a lot slower. You can see that, but it's not having an effect on the volume, right? And if you think about it, even a gas that's 14 times bigger, aren't these gas molecules still all really small to begin with, right? I mean, they're on the atomic scale size, right? They're super small already. So changing the type of gas doesn't have an effect on volume. Adding more gas, though, does. So when you added more gas, increased the amount of gas, the volume got bigger. And that should make sense. That should make sense. If we put more gas in there, the volume, if the volume can expand, then it should expand. And all you have to do is think about blowing up a balloon. If I take a balloon, a latex balloon, and I blow it up, I'm putting a little more gas in it each time. And as I put more gas in, what does the volume of the balloon do? It's bigger. Right? If the volume can expand, it will expand. Right? And that's exactly what happens. So if I triple the amount of gas I add, then the volume itself will triple. So the amount of gas is directly proportional to the volume. Yeah. So that's one of the things. Those are the three things that we looked at yesterday in activity A. Today, ladies and gentlemen, we're going to focus on pressure relationships. So here's what you all need to do to stay in tune with what we're setting up. One, you're going to select pressure as the dependent variable. Okay. Then you're going to raise the volume all the way up to 42 liters. The moles should already be set to 1 mole, so I think you're okay with that. And the temperature needs to be lowered to 100 Kelvin. Okay, you get all that set up. Let's do that, and then we'll take a look at the introduction and the question. Okay, so first things first, what do we do first? Set the dependent variable to pressure. Do that. Then we're going to raise the volume all the way up to 42 liters, right? And the amount of gas stays at 1 mole. So we do all those things. Oh, by the way, put this back on hydrogen. Put it back on hydrogen gas. All right, so we're all set up. We're all ready to go. It tells us that pressure refers to the amount of force that the gas molecules exert on the walls of their container. Pressure always refers to force acting over a specific area. In fact, the equation for pressure is force divided by the area that it acts on. What determines how much pressure will exert on a gas? So we're going to look at pressure relationships today. We set the gas back to hydrogen. We did that already. And what we're going to do is we're going to observe how the gas molecules collide with the bottom of the chamber. Okay, you're going to get a real lesson in terms of what pressure is really all about. Okay, And it's going to have to do with this very first exploration in part 1. Okay. We want to note when we increase the temperature, okay, we want to observe the number of collisions. What happens to the number of collisions? We want to observe the speed of the molecules. And then finally, we want to observe the pressure. Okay. So we're going to raise the temperature and we're going to observe all 3 of those things. Let's do this together. The temperature was set to 100 Kelvin. Okay. What's the pressure, everybody? 0.2 atmospheres. If I raise the temperature, what's going on in the pressure? It increases, doesn't it? What happens to the speed of the molecules? They increase too. What do you think is happening to the number of collisions on the bottom? Didn't they have to go up also? Think about that. If the molecules are moving faster, then wouldn't you have more collisions with that container? Because you have more activity going on. You have more chaos going on. Okay, so what can we say about part number 1? What happens to the speed of the molecules? Temperature increases? The speed increases. What happens to the number of collisions as temperature increases? Number of collisions increases. And then finally, what happened to the pressure as temperature increases? So what is actually going on here? Based on your observations, why do you think pressure increased? Give me a little sentence starter there. Pressure increases because, how about this? Focus on those observations that you just made. Focus on those observations. Why do you think pressure increased? Pressure increases because what? The number of collisions is increasing, right? If the number of collisions is increasing, right, it's going to add to the pressure that is, it's adding to the amount of force that's exerted on the wall, which is adding to the pressure. So pressure increases because the force due to the number of collisions increases. Okay, part 2. What we're going to do in part 2, guys, is we're going to create a graph showing the relationship between temperature and pressure. What we're going to do is we're going to increase the temperature at regular intervals, but I don't think we need to go 50 Kelvin intervals. Let's just go 100 Kelvin intervals, and I think you should be able to see a trend with that. Okay, so go back to the gizmo. Go back to table. Okay, go all the way down to 100 Kelvin. Press record. Let's go at 100 Kelvin intervals. So we're going to go from 100 to 200. Record. 300 Kelvin. Record. 400 Kelvin. Record. And then 500 Kelvin. Record. Okay. So guys, notice the pattern here. When we go from 100 to 200, we double the temperature. Yeah. Look at the pressure. It goes from 0.2 to what? 0.39 is almost 0.40. The pressure almost doubled as well, didn't it? And then take a look again. We're going to go from 200 to 400. Well, the pressure goes from almost 0.4 to almost 0.8. What does that tell us is going on here? Pressure directly or indirectly proportional to pressure? Yeah, directly proportional. Great, please. Therefore, if the temperature is quadrupled, what will happen to the pressure? It will quadruple as well. Part 3 is the summary. The relationship between pressure and temperature at constant volume is given by Gay-Lussac's law. State Gay-Lussac's law in your own words. Okay, I'll start it for you. Pressure is what? Directly proportional to what? Finish the sentence. Pressure is directly proportional to temperature. Easy sentence. Easy sentence. Finish up that sentence so we can start the investigation on part 4. Okay, in the next investigation, we're going to look at volume affecting pressure. So what we're going to do is we're going to go ahead and clear the data like that. You're going to go to bar chart. You've made the, and keep the temperature constant. You keep it at 500 Kelvin. It doesn't matter. Okay, but keep the volume as large as possible. What we're going to do is this. Watch this right here. Do you see the volume bar graph right here? Yeah, you see the pressure bar graph? Watch the volume and the pressure bar graph as we lower this thing. So I'm going to lower the volume. What's happening to the pressure? Doesn't it go up by the same amount? Yeah, pressure decreased all the way from here down to here. Volume, excuse me, decreased here. Pressure increased from all the way down here to all the way up there. So the amount that the volume decreased is the same amount that the pressure increases by. What do you call that? Inversely proportional, right? So gradually decrease the volume. What happens to the pressure of the gas? Pressure increases. What happens to the pressure when the volume is cut in half? What's the inverse of 1/2? Doubles times 2. The pressure will double. Okay. What happens to the pressure when the volume is quadrupled? Well, what's the inverse of quadruple? Quadruple is times 4. 1/4. How does volume affect pressure? volume decreases as pressure increases, and vice versa. And yes, they are inversely proportional. Now let's go to part 5 and create a graph with this. Here's how we're going to do that. I'm going to go all the way back up to having, actually, you can actually start down here. I'm going to start at 5 liters, and I'm going to go up by 5 liters every time. So I'm going to start at 5 liters, and I'm going to press record. And I'm going to go to graph, and I'm going to go up by 5 liters every time. So it's a 10, and I'll go all the way up to 40, 15, record, 20, record, 25, record, 30, well, 31, close enough. 35, 40. Guys, what do you notice about that trend? Yeah, that's a negative slope, isn't it? That's a decreasing trend. So when I go to is the slope of the line positive or negative? Based on the direction of the slope, is the relationship between pressure and volume directly or inversely proportional? They're inversely proportional. Which law summarizes this relationship? You guys are now going to have to pause for a second, go back to activity A, and look at what we summarized yesterday. We summarized Charles' law, Boyle's law, and then earlier on we summarized Gay-Lussac. I want you, and we also looked at Avogadro's law yesterday too. So which one of those laws summarizes the inverse relationship between pressure and volume? See if you can find it. Which one is it? It's Boyle's law. Boyle's law was what we did in part of activity A yesterday, that that summarized the connection between pressure and volume. Part D, do you think making the chamber smaller leads to an increase in gas pressure? Okay, now why? But if you're making it smaller, what's increasing? Don't say pressure. The number of collisions increases, therefore the pressure increases. Right? So by making the chamber smaller, by making the chamber smaller, the number of collisions and thus the pressure will increase. Okay, in the last activity that we're going to do for part B here, you're going to select the bar chart, okay, and we're going to change the number of moles. We're going to start all the way down to 0.2 moles, and we're going to increase the number of moles and see how does that affect the pressure. Do you expect there to be more pressure if you add more gas? Okay, that's fine. Okay, first you're going to clear the data. Go to bar chart. Take the moles all the way down to 0.2. Doesn't matter what the temperature is. Temperature can stay at 500. Who cares? But what you're going to do is you're going to go and you're going to press record. That's the first value. Then we're going to go up to 0.4, 0.6, 0.8, and 1. And if you look at the graph, change the x variable to moles, what do you notice? It's a slight increase, but it's still an increase, isn't it? Okay, you're increasing as the amount of gas increases, the pressure increases. So take that balloon analogy, okay? If I'm blowing up a balloon, you say, well, the volume expands. Well, yeah, it expanded because latex is flexible and it can expand. But why does it expand in the first place? If I blow more gas into it, there are more, what's going on inside? More collisions. If I blow more air into it, there's more collisions. More collisions add more. Volume's kind of an indirect thing. Yeah, you're adding volume, but as I add more gas to it, I'm adding the number of collisions increases, I'm increasing the pressure. And if the container is flexible enough, it's going to increase. It's going to get bigger. Okay, so what happens to the amount? What happens to the pressure as the amount of gas increases? Pressure increases. What is the relationship between the number of moles and pressure? The amount of gas is what? To pressure. This one should make sense too. If you're at the gas station and you're putting more air in your tires, you're adding more air. What happens to the pressure of the tires? It increases, right? It increases. There's more collisions going on, more pressure. All right. In part 7, we're going to make an inference. It tells us, ladies and gentlemen, that 1 mole of any substance contains Avogadro's number of particles. Avogadro's number is this constant value, this super huge number of 6.02 times 10 to the 23. What this means is 1 mole of anything, 1 mole of hydrogen, 1 mole of carbon, 1 mole of iron, 1 mole of gold, 1 mole of I don't care what, contains this many particles. When I say particles, I'm talking about atoms, I'm talking about molecules. Heck, we could even be talking about electrons, right? So any small level of particle would qualify, okay? So this number of particles is found in 1 mole of any substance, okay? And chemists designed the concept of the mole to deal with super huge numbers because it's not convenient to deal with super huge numbers. Dealing with smaller numbers like 1, a lot easier. What do you think is going to happen if you double the moles? How is the number of particles going to be affected? Will doubling the number of moles double the number of particles? Of course, yeah, because 1 mole is this number of particles, so 2 moles would be 2 times this, wouldn't it? Absolutely. Does doubling the number of moles double the pressure? Guys, they're directly related. Yes. Yes, because they are Directly proportional. Part 8. Compare the gas to nitrogen, which is heavier than hydrogen, and observe. Do the molecules move faster or slower than those of hydrogen? Okay, so you got to go to the description tab. Okay, keep 1 mole, keep 500 Kelvin, keep 40 liters. It doesn't matter. Go to description. You see how fast hydrogen is moving, right? Nitrogen is bigger. Is moving faster or slower? Considerably slower. Now, why does that make sense? Look over here on the board. Hydrogen is H2, moves faster, but it's small. Nitrogen is slower, but it's bigger. And if you focus on the kinetic energy equation, 1/2 mv squared, isn't the average kinetic energy measured by the temperature? Didn't the temperature stay the same at 500 Kelvin between both of those? Okay, so why does this make sense? If I am a lighter molecule, I have to be moving considerably faster to have the same kinetic energy, and that's the same temperature. Those two have to balance, don't they? Mass and speed have to balance. So if I am bigger mass, slower speed. But because I've got the same kinetic energy overall, hitting the walls, is the number of collisions changing or the amount of force changing? No, it actually isn't. Is it likely that, so what is it, faster or slower? What did you guys observe? Nitrogen was slow. Since heavier molecules exert more force each time they collide, is it likely that fewer molecules could produce the same force? Yes. Guys, observe the pressure as you change the gas. What can you conclude about the effect of the type of gas on pressure? What's the pressure at? Okay, 1.03 atmospheres. Okay, let's observe that pressure. I'm going to go from nitrogen to helium to hydrogen. It does. The pressure stays the same. Why? Because the temperature and thus the average kinetic energy of the molecules is staying the same. Because there's a balance between mass and speed. That's going on. Ladies and gentlemen, how are we doing so far? Are you doing okay? Okay, almost finished up here. No effect. What are the 3 ways to increase the pressure of the gas? This is how you're going to finish activity B. Pressure, I'm going to start off the sentence for you. Pressure increases as, now here's what you got to do. Look up at the top of activity B. Look at all the different ways that pressure could increase. Give me one way pressure can increase. If the volume does what? If the volume decreases. Good. Give me a second way. When the amount of gas increases. Give me a third. Temperature. Right. So when temperature increases, right. So the pressure increases as temperature increases, the amount of gas increases, and volume decreases. Ladies and gentlemen, take a few moments to finish up your sentence for part 9. Please remember, cross out activity C. We're not doing activity C. Okay, if you don't cross it out, you're likely to forget and then ask me, hey, what are we doing with activity C? We didn't finish it. We're not gonna finish it. If you were here yesterday and you were here today, you likely have activities A, B, and the warm-up finished, which means you're ready to turn this in. If you're not finished for whatever reason, please make sure you finish it before Sunday. We're not doing C. That's right. So go ahead and cross it out so you guys don't forget.